Hello again. Next up at the Data Science and Analytics Specialist track here at PyCon Australia 2021, we're welcoming Matt Kelcey, who's a fixture at the MLI meetup here in Melbourne. During the day, he works as a machine learning research engineer at Edge Impulse, a development platform for machine learning at the edge, because not everything has to be centralized on big servers belonging to someone else. Matt has worked across a range of machine learning domains over the last 20 years, including work at ThoughtWorks, as sponsored today, Google Brain, Wavy, and AWS. Matt blogs at http://mattpalm.com. Today, Matt will be talking to us about JAX, which provides automatic differentiation, allowing extremely high performance machine learning on modern accelerators, all from Python. Matt will be showing us the fundamentals of JAX and an intro to some of the libraries that are being developed on top. So please, a big venue-less hand of applause for Matt Kelcey and high-performance machine learning with JAX.
Awesome, thank you so much. Yeah, this is a fun talk. So I've been on sort of a JAX bandwagon for about 1.5 years now, and it's just getting better and better. So I'm very excited to share this talk. So this is about high-performance machine learning. So there is quite a bit of a focus on the sort of things that JAX provides in terms of making things go particularly fast. There's going to be 3 parts, I guess, to this talk. There's going to be some sort of fundamentals. So we're going to talk about like what are the building blocks that JAX fundamentally gives us. We're going to talk a little bit about some of the things that it provides around multiple hosts, because really scaling up over many machines is the best way we have of running at very high, sort of very large scale. And because JAX is quite simple in what it does, it's sort of very fundamental. We'll touch on a little bit about the higher level libraries that we often use, because JAX by itself may not be enough. Okay, so we're going to start with what is JAX. That's a big question, and I'm actually going to start a little bit with like an overly simplified view of machine learning, because machine learning is a very, very broad field, but for a lot of the work we do, it does sort of boil down to these supervised learning type problems where we have some set of input that we're trying to map to some output, and we're really interested in these functions. We're trying to learn these functions F, and even though it's not the complete domain of machine learning, a lot of supervised learning uses gradient descent these days. It's a big thing. So there's a couple of things we want out of a tool like JAX for gradient descent based methods, and the first one fundamentally is gradients. We need to get these functions and calculate what gradients are sort of described by these functions. And you really can think of JAX as the next generation of a very old tool called Autograde. Maybe not very old, it's about 10 years old now. And because some of the original authors of Autograde, which really pioneered a bunch of symbolic stuff, are actually the authors of JAX as well. So it's fair to say that JAX is the next generation of Autograde. And we need things to go really fast. That's something very data intensive, very compute intensive, and JAX is unashamedly just a really great Python interface for another tool called XLA. So this is the Accelerated Linear Algebra Compiler, which was developed by Google, and we'll talk a little bit more about this. But it's not unfair to say that JAX is just like a front end for XLA, because to be honest, a lot of the heavy lifting is done by this compiler tech, which JAX just provides a very elegant Python interface for. Okay, so let's talk about these two things. But before we get to those, I just want to say that if nothing else, the takeaway from this talk is that JAX is a good implementation of the NumPy API. So if I think about some NumPy stuff we might want to do, here's an arbitrary calculation I'm describing where I've got a dot product between a couple of matrices. I'm adding something. We can actually substitute in, rather than using NumPy, an implementation of these things that is provided by JAX NumPy. And I've done this quite a bit. I've got some signal processing work I do as part of work, and that is all described in SciPy and NumPy. And it's actually been pretty good at just literally porting it to JAX by swapping the NumPy imports to jax.numpy. And with a couple of caveats and small changes, I'm able to make my programs run under JAX instead. Now, why do I care? Well, all the things we're going to talk about that come in this talk about the high performance are suddenly available to me, and they're just sort of transparent. So if nothing else, walk away from this talk right now with an experiment you might want to try where you just literally swap in JAX NumPy instead of NumPy. But let's talk a little bit more detail about then some of the things we've got to. So Autograde, this is the first thing I talked about, wasn't it? Here's a function. It's a pretty simple quadratic, 2x squared plus 3x plus 3. if this was the complicated machine learning function I was trying to work with and I was using gradient descent, I might want to get some gradients for this function for something. So the first thing I want to introduce from JAX is a little function called grad. And what grad gives us is a gradient of a function. So grad takes a function and returns another function where when I call this g of f, I get the gradient with respect to the parameter there. So let's see, 2x squared, I'll bring down the 2, it's 4x plus 3. So the gradient at 3, the gradient at 3 is 15. So this is good. Now this illustrates a real key point about how JAX fundamentally works. This thing that JAX has given us, grad, takes a function and returns another function with the same signature. So we're going to see this time and time again, that the main thing that JAX does is these functional transformations. JAX looks at functions and gives us new functions back that are in some way changed based on what we want it to do. And how does JAX do this? Well, it's based on an idea called tracing, a fundamental idea. So here's another thing that JAX has. It's these make expressions. And what I can do is I can say, here's my function f again. I'm going to pass that to JAX to say, well, make me a new version of this function that's called trace f. When I call this function, it doesn't evaluate it directly. The return of this function is actually JAX's view on what is actually happening inside this function. So you can see here we've got this sort of symbolic representation of the compute. And we don't need to dive too much into this, but you can see there's some things being multiplied and some stuff being added. And so JAX is really about doing these things by tracing. By tracing this function and having a symbolic view of things, we get a bit of insight into how the gradient is being done. So if I do that same tracing again, this time on the gradients, I can see a different function. And so this is fundamentally about how Autograde works. We trace these functions, we do this forward pass, this symbolic representation, which is then manipulated to turn into a gradient. Now there's a really, and again, we don't need to talk about the specifics here, there's some numbers and complicated ops floating around. But there's a subtle point here I want to make that is interesting about functions. This make JAX expression takes a function, as does grad, which takes a function. So you can see here we've already got this nice composability. I take my function f, I wrap it with this grad, which mutates f to be the gradient. I can pass that to a JAX expression. So JAX is really about these building blocks which take functions and give us new functions that we can compose in interesting ways. So this composition of functions is a really big, important thing. Okay, so the second part we talked about was going fast. And the first thing that JAX provides us is some just-in-time compilation. So again, here's our function, 2x squared plus 3x plus 3. Very interesting. One thing that JAX gives us is a JIT. So we can take this function again, our f function, and we can just-in-time compile it to get a new version of the function that is that has the same signature and can be run with the same values and give us back the same result. So in many ways, this is the most anticlimactic slide ever written because it looks pretty boring, but there's a lot of really interesting stuff that happens under the hood with this JIT. And fundamentally, an important part of this is the fact that this computation that's being done here would now be being done on whatever accelerator I have. So even though I've described this compute in terms of just vanilla Python or using that JAX NumPy, if I had a GPU, this would be running just by itself immediately on my GPU, which is an important thing about how compilation works for JIT. And how does JIT work? Well, again, I can talk about looking at the JAX expression. What has happened when I've called this JIT function? We've got our f like we had before, and it doesn't really matter what this f is. It's quite simple here, but this could be a very, very complicated, 100-layer neural network or something. And what's subtly different here is now JAX is saying, I'm going to actually make a call out to this tool XLA. So what JAX has done here is wrapped up, had a look at this function, run through it, built this trace, and then is passing it to this compiler under the hood. And that compiler is very high performant. It can do all the classic things we want from a compiler, a couple of key things like fusing ops together or reordering things, whatever it wants to do, but also most importantly, converting things to kernels that are going to run on the device I have. So this would natively run. XLA will make sure that the compute is then done on my GPU or whatever I might have, TPUs and stuff we'll talk about later. So that it looks like it's such a simple function, but it's doing so much, and it's incredible how much it does. So that's a fundamental thing that we'll be dealing with. Another really important thing with making things go fast that we're probably all familiar with is vectorization. So here's a function that looks a bit scary, but it's a bit arbitrary. I just sort of made this function up. It's some function that does some weird stuff. Don't try to reason too much about what this what this is actually doing. It's got a couple of matrices. It does some along axis mins and maxes. It does a dot product of things, and then it adds a scalar. Like this doesn't actually mean anything. I just wanted to say that there's some compute you might want to do, and here's the result we get down the bottom. Now if we wanted to run this function over lots and lots of data, the common way we would do things is to vectorize stuff. And by vectorizing, I mean we normally think about this idea of adding a leading dimension into our data, so that when we pass it to the compute, a lot of the linear algebra libraries underneath will work a lot faster if you can do things in batching. Now, we're probably all familiar with this idea that when we do add these leading dimensions, we just have to make sure that our code is aware of those leading dimensions and can sort of handle them. So if I was to vectorize myself this function, I would go through and just make sure a couple of things hold. So I can see these axes here. Well, now that I've got another dimension, a batch dimension, I have to make sure these axes sort of move around. I've got a dot product here, and I know by experience that the dot product is okay with having leading dimensions, so I don't need to change anything there. And then I've got an addition of a scalar. So I might be a little bit worried and think, oh, what's the broadcasting going to be? Am I going to make a mistake about something here? But I think if you've done a bunch of stuff with NumPy or any other sort of equivalent compute, you sort of get a sense of knowing how to modify this function to make it batch aware. But we don't need to do this anymore. One of the things that JAX provides is this awesome tool called Vmap. And what is Vmap? Again, it's a transformation of functions. I take my function f, I run it through Vmap, and JAX returns me a new version of my function. And what it does is actually, by using this tracing idea, replums the compute that is expressed by f to automatically handle the leading batch. So now if I have this vectorized f, I can call through with an a, b, and c, which has now got this leading dimension. So I've added an extra 2 here, basically, and I've turned this scalar into a short vector. Now, for that particular f we were just looking at, it's not terribly exciting and interesting, but as things get more and more complicated, this idea that JAX will be responsible for the plumbing of the leading dimension is a really big thing, and it can make this huge difference. Here's an example where I used this, which I thought was really interesting. I had some data. This is some satellite imaging, and I wanted to basically blat out a bunch of augmentations of that image. So, with satellite imaging, one of the classic augmentations we can do is to, sets of 90-degree flips, rotation, and then potentially left and right flips. So I've made this little augment. It rotates 90 degrees by some number of the 90-degree turns, and then it either flips or doesn't flip. It's like a 0, 1. So here's an example. So I pass an image in. I've said rotate one lot of 90 degrees and don't flip. So basically I get this image down here. I can use Vmap to express the compute that I want to do all of these in parallel. So what I'm going to do is I'm going to say, here's my augment function. And what does Vmap do? It adds an extra front dimension, basically. So like a leading dimension to all the arguments. So I'm going to say, here's my rotations I want to do, 0, 1, 2, 3, 0, 1, 2, 3. And I want to pair those, zip those together with all the possible combos of flips. So you can see these eight pairings here between these two correspond to all the possible augmentations. So what I'm going to do is I'm going to say, I want JAX to make a version of Augment that handles batching. But one little thing that I've said here is that I only want you, JAX, to add that leading dimension to the second and the third argument. So this is this rotation and flip. But I don't want you to plumb that extra dimension for the first argument. So I've said none here. And what JAX will do is basically broadcast that image multiple times. Now when I call this function, I get this result, because what's happened here under the hood is that JAX is zipping basically across these. And it's going all the way through. It's going all the way through down to these functions to make them vectorized to do that, which is really cool, I think. So now when we call this image all combos augment, rather than just getting one image back, we get 8 images back. Now, I might actually also want to do this whole thing in batch as well. So I want to actually start with a set of images, not just one image, but I might have like 10 images. And I want all 8 combos for those 10. So I've got my all combos augment, which was Vmapped. I'll just Vmap it again, because what does Vmap do? It takes an arbitrary function and just adds another batch dimension at the front. And because I know that this is sort of the level of compute I want to deal with, I might ask JAX at this point to also JIT. So go through and now take this compute that's been expressed by a Vmap over a Vmap with these sort of fixed values, and do whatever you need to do to compile it to make it really fast. And this is blindingly fast. The code it ends up being resulting runs very, very quickly. And this is a pattern I've seen a number of times now. I have this sort of, if I'm vmapping something and I have extra batch dimensions appear, I don't need to be scared. I just keep wrapping with vmaps and everything is fine. So that's really cool. So fundamentally, Vmap does this by replumbing and sort of completely re-changing what my function is. Very handy. Quick side note on TPUs. So TPUs are Google's ASIC custom designed sort of replacement for their in-house GPU farms. TPUs, come in a couple of different sort of models. The third generation, the smallest TPU board I can get, if you renting one basically from the cloud, is this V38, and the 8 corresponds to the fact that a TPU board like this has 4 chips. Each of the chips has 2 cores, so I've got 8 cores in total. What's interesting about this is when you rent these TPUs, that's the minimum you get. You've got no choice. Each of these 8 cores is pretty powerful, but you can't go any lower than that. So that's interesting. And Google provides these TPUs in these sort of boards like this, or in these huge fat combinations of boards with this crazy interconnect, where that's called a pod, where you have hundreds of these TPU boards put together to make effectively 2048 cores. Now, the reason I bring this up is because the development of the TPUs was done hand in hand with the development of XLA, which is the compilation technology we talked about. XLA was sort of introduced at the same time as an intermediate between the code being run either to GPUs or TPUs. So XLA is very much around making high performance code for TPUs, and JAX is in many ways a front end for XLA. So we're going to get a lot of really huge benefit from using JAX very, very simply across these very large compute clusters. And it's quite astounding what you can do nowadays that even like a couple of years ago was quite difficult to sort of orchestrate. So I'm going to introduce another concept called Pmap. So this is parallelization rather than vectorization. And if you go right now to Google Colab and you start a Colab, you're allowed to just get a free TPU. So if you sort of pick device TPU and you just sort of import JAX, maybe there's some stuff you need to do, but it's basically import JAX. You'll get JAX has a view over these 8 cores. So rather than just a single one, we've got 8, and JAX provides us some tools for making use of this. Here's an example of how Pmap works. Here's a function. It's very simple again, ABC. We'll just add them up, and we're going to Pmap this function like we did with the Vmap. And Pmap takes a function and it gives us a new version of this function that can run. And it's again, this idea is that there's a leading dimension which is being put on top of things. So if I have some A and B which are 8 by 3, and I'm on this TPU machine which has 8 cores, then when I run this compute, I'm actually running this computation in parallel, each of these rows being run on its own device. So what JAX is doing here is it's a little bit different to Vmap. Vmap, we actually replumb the code. Pmap actually takes this function and actually does a compilation of it and ships it out to the devices we have. So if I have this V38, which has 8 devices, when I call this Pmap, I'm actually compiling this code, sharding this input, and actually sending it out to the devices, and all the devices do things in parallel. And it's not until I actually instantiate it in some way, in this case printing it to my screen, that the result is actually brought back from those devices and assembled. And that's why we see this here, sharded device array. Because until I actually do something and act on it, it turns out that actually each of these rows lives in the memory of the device. So this is really important because if you've done much with like multi-machines, you really need to make sure that the data being shipped around versus the code being shipped around is under your control, because sometimes you don't want to just be sort of wasting time moving memory around when you don't need to. So Pmap gives us a lot of control over how we're sort of sharding data versus the actual compute. And it gives us actually more than that as well. It gives us a bunch of collective operators. So I'll go through this one pretty quickly. It doesn't, there's a couple of details here we don't care too much about. But if I'm doing some machine learning over a large number of machines, so again, this huge cluster of 2,000 machines, I might have some sort of loss function where, I'm passing in parameters and I've got my X and Y. Reintroducing some of the concepts we've talked about, I might want to calculate gradients for these parameters with respect to this input and output. And how would I do that? Well, I can take my loss function. I can ask JAX to give us the gradients, and I can ask JAX to please make that fast in whatever way is required. And at this point, if I've Pmapped this function, At this point, each of the devices, if I passed a shard of X and Y, would be looking at a different set of gradients. So the thing that Pmap really is about is this parallelization. So this piece would all be running in parallel across the machines, and each device, as long as the X and Y was separate, would be like gradients for a different chunk of my data. Now, in a very, very simple way, JAX provides this other operators which work across the mesh, in this case psum. So by simply running this psum here, what JAX would do in this case is across all the devices actually collect the gradients together and sum them up. So if I had 2,000 machines and each of them had individual gradients, at this point if I collect them together, I would actually sum all those gradients up, and depending on how I wanted to use those, I would either use psum or pmean. And behind the scenes, JAX is doing all the work to have all these machines interchange and to sum and to put things together, and we just get it magically. So this is huge because trying to do this stuff yourself is a complete pain and requires so much code. But JAX just makes it absolutely trivial with these type of operators, and it just scales from the TPU with a v3.8 up to these TPUs pod slices with literally thousands of cores without any code change. It's quite astounding. And Pmap and Vmap sometimes feel like they're quite specific, and JAX is very much a moving target. I love this. This is the next version of Pmap potentially, which is called Xmap. And I love this. This doc string is aspirational. It's just like JAX really is bleeding edge some of this stuff. But they're providing more and more ways to make use of this crazy compute and to give hints around how you want to actually make use of these meshes. It's quite astounding. Okay, so everything we talked about here is quite low level. We talked about there's vectorization and parallelization. It's fun stuff to do, but it's nothing to do with how we usually do things. So a lot of people ask me, do you like JAX or Keras better? And they're a little bit it's a bit of a mismatch. You can't really make this comparison. And for me, Keras is two fundamental things. It's a way of describing model definition. So a really rich way of assembling what they call layers into models and the sort of optimizers that would go with these layers and models. So that's a really handy thing Keras has. And another thing that Keras is very good at is having an opinionated fit loop. So this idea about given some data and an optimizer and a model, just sort of run in batches over it and do things with control from callbacks. So Keras really has those two things, and none of those are anything to do with JAX. JAX couldn't care less about fit loops. It couldn't care less about optimizers, although it does have some sort of reference optimizers in the experimental sort of branches and modules. But fundamentally, JAX is around that making use of XLA to do this great compute. So if you provide an awesome library for doing this sort of stuff, but you don't have higher level libraries on top, what happens? You get the Cambrian explosion of libraries, and this we see time and time again. So if you wanted to do anything with JAX, you probably don't want to do it directly with JAX. You want to do it with one of 50 million different libraries that come out all the time, and they have different flavors and sort of different separations of concerns. Like RLAX is interested in reinforcement learning, TRAX is interested in transformers, JAX-MD is like using these meshes to do complicated molecular dynamics. So really, it's hard to decide which library you might want to use on top. The only thing you can really do is to explore and experiment in a couple of different ways. The one that I have sort of settled on myself is the combination of Haiku and Optics, and I just want to give you a quick flavor of those. So Haiku has, like I mentioned with Keras, one of the things that Keras gives you is a way of defining layers into models. That's a really big thing. And Haiku gives us a bunch of that stuff. So here's the simplest model I can basically make. This is y equals mx plus b, basically. It's a linear layer that Haiku provides, and there's some function which describes that model. But this function I've got here could be all sorts of things, multiple convolutions, all sorts of weird self-attention stuff. Haiku provides a whole bunch of what we think about as those layers that I can assemble in different ways. And then what we get from, and again, I'll just point out some interesting things here. What Haiku is doing is taking these functions and in the same way JAX does, transforming them into other things that we can use. And in particular, the main one around the model definition is that Haiku will change this function into a model object, which has two important things for us. One is an initialization sort of idea. given this model, and through tracing, what does this model do and what parameters are used by that model. So the first thing we want to basically do is to initialize this model to get a sense of what are the actual parameters that are described inside. And then once we have those parameters, we can apply those parameters and some input to get an output. Now you can certainly see this is very much the functional way of doing things, isn't it? Usually when we think about like an object-oriented approach, we would sort of bake these parameters into the model. But Haiku continues to use that functional approach of saying, well, it's really about everything's with respect to parameters every time we make these calls. So if you're more of a functional sort of person and you want to use the JAX stuff more directly, which is definitely about functional stuff, then Haiku is maybe better. Whereas if you want to try to hide things more and more and you're not as interested, then there might be another library that would suit you better. The other thing that sits next to Haiku, which is a different package, is a tool called Optics. And Optics is a set and a collection of optimizers. So in the same way that, say I wanted to use Atom to do some optimization, what I would do is I would make one of these Atom objects, and I would initialize it, again with these parameters that have come from my model. And that gives me an optimizer state, because some optimizers are stateful. Atom, for example, is a stateful optimizer. And then it's up to me again to look after this state and to do things with it. And in particular, here's the classic update rule we might do. I'll go through this slide a bit more carefully. So I've got some sort of loss function that describes, given a set of X and Y and a set of parameters, how well am I doing? And the way I would calculate that loss is to apply my model with the parameters in X, get predicted values, and then calculate some sort of loss. Then what I can do is use JAX to get gradients of that function with respect to parameters, which give me gradients. And then what I can do is pass the gradients to the optimizer to say basically, given these gradients and your current state, what's your new state? And are there any updates to make to the parameters? And then again, given the parameters and those updates, what are the new set of parameters? So this is a classic sort of functional approach again, where we're passing in states and getting new states back. So all these things are 100% immutable, and we just sort of have to do this classic thing of here's a set of parameters, and through this update, I get a new set of parameters. And we're using all these JAX fundamentals like grad or jitting this entire thing. But all these things that I put in here, depending on how I want to do things, can have a sprinkling of the Vmap and the Pmap, depending on how I want to run across different machines. So you remember in that slide a little while ago, we were talking about this update being done with a Pmap instead of just directly with an update. And I think this idea of being able to introduce these things as we go along is super powerful, because what it means is that we can sort of get things working in a simple way on a sort of single machine, simple non-batched sort of operation, and then eventually scale things out more and more and more. And this idea of jitting an update rule and then basically going through and then just pumping that update basically across the data set, where we pass in parameters, we get the next parameters, we pass in the state, we get the next state, and just sort of run that is very, very fast, because we're basically just sort of, if these are sharded across the devices, then the only thing we're having to do is really move the data around. So this can be very, very high performant at a very high scale. So yeah, just a recap of the sort of things we talked about. I sort of talked about the JAX fundamentals. That was the main thing. And again, that takeaway, just try JAX NumPy if nothing else and see how you go. It might just work and surprise you. But fundamentally, there's these building blocks that JAX provides around the classic sort of composition. So gradients, I want JIT, I want a Vmap things. There are some multi-host specific things that come from the sort of heritage of why JAX even came out around XLA. And so there's things like Pmap and Psump. And I've scratching the surface here. In terms of that mesh computation, there are many, many complicated things that we can do here. I've just sort of dropped into, for a quick talk, this idea of parallelization on map, or this operator Psum. And then, JAX maybe isn't exactly what you want. You want a high level support. And all I can say is just query what the latest neural network library for JAX is, because it would have changed by the time this talk is finished. It's a very vibrant field with a lot of things changing. And, I think it's okay in these sort of fields when things are fast to try a couple of different ones and just see which sort of one represents the way that you think about the problems. And, you might get lucky on one, or you might have to change around a bit. Okay, so that was basically my introduction. There's like a 2-hour version of this talk with a bit more tutorial stuff on my website there. But otherwise, here's a bunch of links which correspond to the sort of things I've talked about so far. Thank you.
Thank you, Matt. And so we have time for one question, and it's going to be a quick one. Maybe you have a quick answer. So you've mentioned TPUs, but most people have GPUs or no GPUs. What kind of problems are better trained on TPUs? Like they would require you to go the TPU way, and would your JAX code change for that?
Yeah, so the JAX code would not change at all. So they've been very clear that XLA supports GPUs as much as TPUs, and so all the things I talked about, Pmap, Psum, they work on my desktop here with a couple of GPUs without any change at all. The TPUs are, yeah, the TPUs I think are more sorted. In terms of the benchmarks I've seen, the TPUs are the best performance when you're really starting to get into the large data regime. So generally, the way they work is that like a lot of like high performance accelerators, they work well once they've got a real chance to spin up. So if you're working on a small bit of data, you might find that JAX on TPUs isn't actually as performant as some other things, and it's not until you get to these bigger data sets that it really makes a difference. Particularly batch size is a big one.
Thank you. So thank you so much, Matt, for being part of the Data Science and Analytics track today.
Yeah, no worries. Thank you.
And coming up at 11, we'll have Jyotika Singh, who will be talking to us about classifying audio into types using Python. See you then. Bye.